In our previous video, what we did was we derived the algorithm for the incremental search. And so in this video, what we're going to do is we're going to program an algorithm in using MATLAB to be able to find the zero or the root of a function. So let's take a look at this function, okay, just as an example. And let's have the step size 0.005, all right? And we're going to go ahead and we're going to ask the user to input all the components that comprise the incremental search. So the function, then we're going to graph it, then we're going to get an upper and lower bound and an incremental size. And then we're also going to solve the function, the zero, or approximate the root using the lower bound and the VPA solve function. All right, so let's just do this part. Then we can go ahead and use the algorithm, the incremental search stuff. So with CLC, I'm going to clear all, and I'm going to sims a variable x because I need to use my easy plot. And let's just go ahead and say f is going to be the input where we get the function from the user. So enter a function in terms of x from the user. And then we're going to easy plot that function. And then once we easy plot it, we're going to get this XL, which is going to be the lower bound, and we're going to get an XU, and we're going to get a step size. All right, and I'm just going to say input, and we're going to say enter a lower bound. And then we're going to go ahead and enter an upper bound. I'm just going to copy this and say upper. And then I'm just going to say enter a step size. All right. Now I'm going to use the VPA solve function. Okay. And we're going to say VPA solve. And I'm going to call that the actual, even though I know it's not a precise value. But what we're going to do is we're going to solve for where f is 0. Okay, so remember, we're trying to find the root. So remember, back up here, what we're trying to do is we're trying to find this root. That's where the function is 0. We're going to solve it for x. And then we're going to use the lower bound as our guess. All right, so that's just the VPA solve function for roots that we can't necessarily, or equations that we can't get an actual value from. We're just going to approximate. Okay, and then I'm going to printf the actual solution. Okay, so say actual solution is %f /n, actual. All right, so let's go ahead and just run this, okay? And that's actually the first 5 parts of this, okay? So let me suppress all this stuff because we really don't need to see it. All right, so now it might take a minute because it's the first time we're running it with a plot. All right, so just be patient if you want to fast forward just to see what it looks like. So I'm going to enter the function. Remember, it's e to the x minus 3. And I forgot to suppress it, but no big deal. Here's our plot. Okay, I'm going to put a grid on this thing. And I'll just say something like 0 to 15. All right, because we really don't know right now. So I just hit 0 and enter. And I'm just waiting for this thing to run again. I think it's running. There it is. I'll say 15. And I'll say 0.005. And the actual solution is not there. Okay, so it didn't print out. I don't know why. But maybe when I try to run it again, it'll come off. Okay, so let me go ahead and put a grid on this. Let me get rid of this guy. All right, and let's try to run this again. All right, so I'm going to go ahead and execute it. I'm not sure why the actual solution didn't come out. Okay, but let's give it a try again. All right, so we have our exp of x minus 3. And there's the echo print. I forgot to suppress it. If I zoom in on this, it looks like that we have a couple solutions, but I'll just pick this one. maybe like right here at like one, between 1 and 2. So remember, that's our bracketing method. We just pick an interval where we think that the solution is going to lie. So I'm going to say 1, and I'll hit enter, and hopefully this thing runs today. I'm going to close this because we don't need it now. And MATLAB's just taking its good old time. So we're going to say 2, and I'll say 0.005 for the step size. All right, so this time it actually did print the actual solution. Okay, so 1.505, which is feasible. All right, now at this point, let's go ahead and program the algorithm. Okay, so we graph the function, done, and then we estimate XL and XU. Okay, done. Okay, that's from the graph. We also develop a step size that's given to us, done. Okay, now we're going to program f of XL and f of XU, and we're going to see if it's greater than or less than 0. Okay, so I'm going to call that product, and product is going to be equal to where we substitute f comma x comma XL, and then we're going to multiply that by subs f comma x comma XU. All right, now, if that value is going to be less than 0, okay, we're going to keep repeating this process. If it's not, then this is where the solution lies in this interval. Okay, so we're just going to keep doing this until we get a number that's bigger than 0 for product. So I'm going to use a while loop. So I'm going to say while our product is less than 0, I'm going to compute a new product using the next step. Okay, so the next step I'm going to call x, which is going to be XL. Okay, and that's how we get this right here. We say XL is going to be XL plus H. And then I'm just going to compute what the product is again. Okay. Now, it's going to keep doing this because we really don't care about what the number is, all the numbers before that. We just care about until we get to XL. And once we have that value of XL that's just before the 0, okay? So remember, we're just incrementally finding all these values until we get to two numbers that are positive. Then we go back and we say, okay, the solution lies somewhere on this interval between these 2 points, okay? So that's what we're going to code now. Okay, so we're going to say that f print f, and we're going to say the solution lies between, and I'm going to say bracket %f, comma %f. Right. Keep using the wrong characters. Sorry about that. And I'm going to say /n, and then I'm going to use our algorithm where we have XL minus H. That's going to be XL minus H, comma XL. All right, so let me go ahead and just run this, okay, and show you what happens as we run it. All right, so same thing's going to happen. The graph's going to come up. So we have our EXP of x minus 3. I'm going to copy this because I'm sure we're going to run this a few more times. Okay, then I'll hit enter. All right, and we have our lower bound, which we say is 1 from the graph. Then we have another lower bound, which we say is 2. Let's use 0.005. And our algorithm runs, it runs, it runs. Might even do something. You might want to fast forward just a little bit just because there's our actual solution. And then here's the interval using our incremental search where the solution lies. Right? Now, to get a singular value, I could just average these two numbers. All right, and that would tell me an average of where we think the solution lies. Okay, so I'm going to say that the approximate is going to be equal to XL minus H plus XL. So that's the sum of the two bounds divided by 2. And I'm going to f print f, and I'm going to say that the approximate value is %f /n, and I'm going to call that the approximate. Okay. And then finally, I'm going to find the percent error. So the P error is going to be equal to our approximate minus actual, which we found a long time ago, divided by actual. I'm going to multiply that by 100 and suppress it. And then finally, I'm going to say f print f, and I'm going to say the percent error is percent f / n, comma, P error. All right. So let's give this a go and see what happens. Okay. So just all the same stuff. Nothing's going on different. Okay. I forgot to spell the correctly. Oh, well. All right. So there's our function. And we know the lower bound's 1. All right. Here's our graph. It's the same graph as before. No big deal. I'm just going to get rid of it so we can see the code, which we really care about. 1, 2.005. Eventually, and unless I spelled something wrong, we should be okay. Oh, spelled f print f incorrectly. All right, so that was in line 21. So apologies. You all probably saw that a while ago. All right, let's run this again. All right, so there we go. Wish this would run a little bit faster, but looks like my computer's just running slow tonight. All right, so there we go. All right, so check this out. So what we did was we took the average of these two numbers within our bracket, which was this value, and then we found this was approximating this number to be able to get our percent error. All right, now let me show you what happens if we were to decrease the step size and make it like 0.0005. All right, so let's just run this one more time just for fun. I'm going to get rid of the easy plot just because I don't feel like it running just to get the plot for this. We already know the bounds. All right, so let's run it. And that's probably sucking up a little bit of our time. So here's our function. And lower bounds 1. It's still plotted. Not sure why. Oh, because I put the grid on. That's why. So there's our lower bound. I probably should have put a percent up there. Our upper bound's at 2. And it might take a little bit longer if we use 0.0005. All right, let's just see what happens, just for efficiency. All right, so there's the actual. It's taking a little bit to run because we decreased the step size. All right, but check this out. By decreasing that step size, we got a number that was pretty close. Okay, so we got a lot closer than what we did before. Okay, percent error. Remember, this is a percent error. Okay, this is 0.0000565%. Right, so that's really accurate. Okay, so that's our incremental search method. Okay, it's literally just using a bracketing method, and it just keeps getting closer and closer and closer until we get two numbers or two guesses that are positive. Then we revert back to one that was negative and one that was positive. And by our intermediate value theorem, we're guaranteed a solution. All right, so in our next set of videos, we're going to be taking a look at the bisector method, which is a little bit more efficient, but also a little more difficult to implement.